Awesome. Thank you, Alvaro. Okay, so today we're going to talk about curves of higher genus. And so yesterday we talked about elliptic curves, which are curves of genus 1. And if you don't know what genus means, that's fine. We're going to define it. So there was some question on Piazza, which is about algebraic geometry background, and that's a totally fair question. And I like struggled a lot with like how much background is required. So I've tried. So whatever I've tried to make it like self-contained in that algebraic geometry background would be good, but not absolutely necessary to understand some of most of the things in the course. So and in the sense that if you I've tried to put some of the background that you need in the exercises, for instance, right? So yesterday we were talking about function fields, right? And with maps of curves, one very important thing that comes up is the corresponding extension of function fields. So I've tried to put some of those in exercises in the at the end of the lecture notes. And so if you don't have a background in algebraic geometry, then or if you've only seen a little bit of it, then you might find it useful to go through those exercises. There was also a discussion on Piazza, and people suggested reading the first 2 chapters of Silverman. And honestly, if all you do during this entire time is read like 2 chapters of Silverman, that's a great thing to do. Trust me. Um, so the other thing that I was planning to do, and maybe will be useful, I don't know. So today, and maybe tomorrow as well. So we'll see about tomorrow later. But today at 5:30 p.m. Eastern time, I will be in the Blackboard Collaborate room. And I will answer algebraic geometry questions. I mean, of course, if you have other questions, I'll also answer those. But if you have any questions about like the algebraic geometry background required or any particular function field questions, you can. I'll be here. I'll be there from like 5:30 to 6 at least. And you can come visit the room and ask me any questions you have, right? Okay. So hopefully that's somewhat helpful. Great. So today we're going to talk about curves, right? So general curves. So a curve, so what is a curve? So a curve is a variety, so it's defined by equations, right? So it's an algebraic variety of dimension 1, right? So this means that locally things look like a line, right? Calculus. So for us, most curves are going to be the following, right? So unless mentioned otherwise, like sometimes I'm going to talk about A1, but for us, most curves are going to be smooth, projective, and I'm going to add in some other adjectives, and we won't worry about those adjectives, right? So absolutely irreducible, geometrically integral, right? So we're not going to worry about these adjectives right now and what they mean. All you need to think of is that you have a nice curve, right? So most of the things that you want to be true are true, right? So you can write down equations for them. So smoothness is something that will be important, and projectiveness is something that will be important, right? So these you don't have to worry. So absolutely irreducible basically means that if you base change to the geometry to the algebraic closure, then your curve does not look like this, right? So it doesn't look like a bunch of curves put together. And geometrically integral has some other stuff. Anyways, so it's projective in that it can be embedded into some projective space, right? But a lot of the examples that we're going to do are going to be, so our examples are mostly going to be curves in P2, right? Which means they're going to be defined by homogeneous polynomials of in 3 variables, right? So x. y, z. And then we're going to dehomogenize them like we did elliptic curves. And so effectively, you're just going to have two variables to work with, right? So let's do some quick examples. The first one is the general class of these curves that I was talking about here. They're called plane curves, right? So plane curve of degree d is defined by a homogeneous polynomial of degree d inside P2. Okay? And so what this does, and so after dehomogenizing it, what you can think of is just an equation that looks like aij x to the I y to the j equals 0, right? And so this is after setting z equal to 1. And remember, yesterday when we were talking about elliptic curves, we also looked at z equal to 0, right? So let's call this curve C. So you can also, if you set z equal to 0, C intersected with z equal to 0, right? This is going to give you some solutions, which we don't see here. And these are going to be called the points at infinity. Right? So let's look at some other plane curves. Another class of curves is called hyperelliptic curves. So this is a generalization of elliptic curves. Right? So these come with a degree 2 map to P1. And they admit a model. So they admit an equation. So as we saw yesterday, equations giving a curve are not unique, right? So you can like make transformations and move around variables. So these admit an equation that looks like this: y squared equals fx, where fx is well, we're over fq, so it's a polynomial in fq that is square free. An elliptic curve is a special case where f has degree 3, but in general, these could have higher degree. And the map to P1, right? So the map to P1 is given by sending xy to x1. Okay. So it might be useful for us to dwell on this a little bit and look at what happens to the corresponding extension of function fields. So what happens to the function fields, right? So what is this induced map, right? So here, what are we looking at? We're looking at KP1, and we want to look at what it looks like inside KFC, right? Now, what is KP1? These are functions on P1, right? And you can sort of, if you ignore the point at infinity, what are functions of P1? Well, okay, so there's a question that says the degree of a map is defined as the degree of the extension of the function field. Yes, that is correct. So the degree here again, yes. So the degree of the map, this is equal to the degree of the extension of function fields. Right. That's correct. Great. So this is a quadratic extension of function fields. So now let's go back to understanding what KP1 is, right? So KP1, well, it's basically a line. So what are functions on a line? They're polynomials, right? So this is just going to be polynomials in one variable. And KC, well, you're going to have KX. And now notice what you're doing over here, right, with this equation. What you're doing is you're taking fx and you're adjoining a square root of fx, right? So k, oops, my bad. So kc is kx adjoin the square root of fx. Right? So this is the corresponding extension of function fields. And what you should compare it to, you can compare it to the corresponding extension q inside q square root d, where d is some fundamental discriminant, right? So, or some square free integer, whatever. Okay. And so one thing that you might want to understand is over here, well, the primes that divide D are ramified, right? So primes that divide D are ramified. And maybe you want to ask what happens in this extension. Sorry, ramified. And so maybe you want to ask what happens in the extension kx embedded inside kx adjoin square root fx. Right? And so if you maybe go back to commutative algebra, then what are primes inside a field or inside a polynomial ring over a field? Well, the primes are the irreducible polynomials, right? So here primes correspond to irreducible polynomials, right? And so, oops. And so the things that will be ramified here will come from the factors of fx. So ramified primes are going to correspond to factors of fx, right? So irreducible factors of fx. Now, well, you could try to, so if k is large enough, right, then fx splits, right? So what you can think of, so this map C to P1 is ramified at the roots of fx. Right? So another way of thinking about this pictorially is the following. So if you try to, so this is like, another way to draw this is the following. So you can think of P1 as like being a line, and C is some curve, and then it's got some points. And these are the points, right? So because C is given by y squared equals fx, in general, if I take a point here, if I take some value of x here, the two roots of fx give you these two values of the two square roots of fx give you the two values here and here. And the ramified points are where these two roots collapse and give you the same point. Right? So in terms of the degree, in terms of the extension of function fields, this is the picture you should keep in mind, right? And the ramified points are the points where fx vanishes, right? Or where the roots above the map are the points above the map sort of collapse to give you 1 point. Okay. So if P, so I should say here that this is hyperelliptic if P is an odd prime, right? So if you're over so hyperelliptic if the characteristic is odd. An even characteristic, you have some other form. Okay, and the third example, which I'm not going to dwell on too much, but so this is what is, so this extension of function fields is tamely ramified, if you've seen a little bit of algebraic number theory. There are wildly ramified extensions of P1, and these are called Artin-Shire curves. So Artin-Shire curves, which in characteristic P, right, are given by y to the p minus y equals fx, where fx is a rational function. And this happens to be a wildly ramified cover of P1. the map is the same. You send x, y to x. Okay, great. Okay, so now we're going to move on to divisors on curves and points on curves. So before we go on, are there any questions?
There is a question in the chat. Is the degree of the map defined as the degree of the extension of the function field?
Yeah, I think I answered that. So yeah, so it is. So whenever you have a map of two curves, the way you define the degree of this map. So maybe I didn't put this in the notes, but the degree of v is defined as the degree of this extension of function fields. I'm gonna add it. Thank you. So I should say that here you need a surjective map, right? All our maps are going to be like at least so surjective on FQ bar points, right? So you need so technically what this is called in algebraic geometry is a dominant map, right? So but you for our purposes you can just think of it as a surjective map. You don't have to worry about dominant. And so because otherwise this induced extension, it doesn't induce, if you don't have a dominant map, then it doesn't induce an injection on the corresponding function fields. So we're going to assume all of our maps do this kind of thing. Awesome. Okay, great. So now we're going to go on to talking about divisors on curves. Let's see. Okay. So C is going to be a curve over FQ for us. A lot of these definitions make sense over any field, right? So the definition of divisors, degree, etc., they're going to make sense over any field. But all of the point counts, for instance, like we're going to be interested in counting points on curves. So that will only make sense. Well, in this case, that will only make sense for finite fields. Okay, great. So let's say you have a point inside C of FQ bar, right? We will define the degree of a point, right, to be the degree of the minimal extension of FQ over which this point is defined, right? P is defined. So for example, if you have again a hyperelliptic curve in odd characteristic, right? If you take an x for which fx is not a square, right? So if you take this point, x comma square root of fx, can be defined over a quadratic extension, right? So if fx is not a square in FQ, then this is going to be defined as a quadratic over a quadratic extension, and so this point is going to have degree 2. Right? So a quick exercise. So this is marked as exercise 2 in exercise 8 in the lecture notes. So a quick exercise is to find the number of degree n points on A1 FQ. Right? So A1 basically just means the affine line. Yeah. Okay. So hint is use exercise 7 plus Mobius inversion, which you learned in the last lecture. Right. So Brandon talked about Mobius inversion in his lecture, so you can use that in order to find the degree endpoints on A1. It's quite a fun exercise, actually. Okay, great. definition, what is a divisor? A divisor is a z-linear combination of points. Right? So you can write it as a formal sum, NPP, where P is any point on C, right? So it can be defined over any field. And what are the few things we demand? Well, the NPs have to be inside Z, of course. And all but finitely many, you want this to be a finite sum, so all but finitely many are 0. Okay. Many NPs. Okay. And so just as there's a notion of a point being defined over a field, there's a notion of a divisor being defined over a field, right? So let's do an example. So notice that here, your points can be defined over any field, right? But so you have a Galois action. So Galois, let's call this D. And suppose you have sigma inside the Galois group of FQ bar over FQ. Then you can construct sigma D by basically applying sigma to all of the points, right? So it's some Galois group, and you so some element of the Galois group, and you just apply sigma to all of the points. Excuse me. And D is said to be defined over FQ if sigma D equals D. Okay, okay. So here is an example. Our favorite example is going to be a hyperelliptic curve because it's so easy to work with. And we're going to take D to be the points x square root of x and, plus x negative square root of x. Right? So now if fx is not a square, right, then each point is defined over a degree 2 extension. Each point is quadratic. Right? But D itself, right? So D, however, D is defined over FQ. And the reason for that is that if you take any Galois element, the Galois element will permute these two, right? So it'll switch these two, but the sum still doesn't change, right? So it's still defined over FQ. Awesome. And so there's a notion of the degree of a divisor. Right? This is defined as, well, if D is a sum over NPP, then this is just sum over NP degree P. Right? So so for example, this one, this is a degree 4 rational divisor. FQ rational divisor. When I say rational, I mean defined over the base field. Awesome, great. Okay, what is another way to generate divisors? So let's talk about that. So let's say I have, examples of divisors. These are important examples of divisors. Let's say I have a function, so a rational function on C, right? So if you want, you can think of C as being a plane curve, in which case F is it's a ratio of two polynomials, right, of the same degree. Okay. Is there a lag in what I'm writing? I feel like there's a lag.
Maybe a little bit. Can you write something? Hello? Oh, there.
I think it's on. It's on and off. It's fine.
I think it's okay.
Okay. So what you can do is, that's weird. Okay. So there's an echo again. Sorry, my bad. Great. So what you can do with f is take something called div f, which is defined as, sorry, it doesn't echo. Can everybody else also hear the echo?
There's a little bit. It's not too much. Did you change the? Did you change what? Where the microphone is?
All right. No, not better.
How about now?
Is that?
That's
Wait,
better.
I'm muted.
No, no, you're good.
Really?
Yeah, yeah, I can hear you. I can hear you.
You can hear me?
Yeah.
Oh, wait. Sorry, give me a second. My bad. Okay, definitely better.
Oh, now there is a. Okay.
Ah! Okay, how is this? Nope, not good. Okay, I'm just gonna do this.
It works.
Okay, hopefully this works.
Yeah, yeah, looks good.
Okay. Oof, technology. Sorry. Um, so the way you construct the divisor is you take the order of um, the function at p and then multiply it by p, right? So what this means, so what does order mean, right? So if ord p, so if f has a 0, right? So if f has a 0 at p, then this is the order of vanishing. The order of vanishing, right? And if f has a pole, right, then it's negative of the order of the pole. So div f has some positive things and some negative things, and the positive things come from the zeros of f, and the negative things come from the poles of f, right? So I think I have time to do a quick example. Um, so if you look at y squared equals x cubed, or let's see it. Let's look at an elliptic curve, which I'm going to write this way. And I'm going to consider the rational function x, right? So x is you can think of as a function in this because it's an element of, well, the fraction field of kxy adjoin y squared minus fx, right? Where fx is this whole function. Ooh, let's call it g of x. Okay, so f is going to be this function x. Now, where does x have zeros, right? So if you write this as x cubed plus ax plus b, right? Then x has zeros when y is like plus or minus square root b, right? So x has two zeros, p1 and p2, right? And right, so if it's if the 2 points are the same, then I'm going to count them with multiplicity, right? And if x, and the question is, where does x have poles? So remember that little x was capital X over capital Z, right? From before, we had like, this is like, because this equation is the dehomogenized version of something that was in projective space, right? We'd like said we divided out by Z, etc., etc. So so this, you can show that it actually has a pole of order 2 of order 2 at infinity, right? So infinity is the point where Z is 0, right? And so you can show that um, this function actually has a pole of order 2 at infinity, right? The order 2, I'm going to leave as an exercise. Okay. Great. So the divisor corresponding to x is p1 plus p2 minus twice infinity. Awesome. Great. So here are some exercises. Oh, wait. No, it's fine. Okay. So first one, so I'm going to define div 0 as the set of divisors of degree 0, right? And you can see that this actually forms a subgroup.
Soumya,
Mm-hmm.
there's a question. Is f equals x different from the variable x that is used to define the elliptic curve?
No, it's the same.
The same.
Yes. Yes, yes, yes. That is crucial. So you can think of x as being a function on the elliptic on the elliptic curve by thinking of it as an element of this field, right? So kxy mod y squared minus g of x, right? That's the ring of functions on E. Great question. Okay, so div 0 forms a subgroup of div C, and div C is basically the set of all divisors. All divisors, right? And because I'm defining them as a formal linear combination, you can always like add and subtract these. And div 0 is a subgroup of these, and they're like the ones that have degree 0. And the second one, right? This requires you using that C is projective, right? That if D is a principal divisor, sorry, if D comes from a rational function, we're going to call this a principal divisor. Then degree of D is 0, right? And so you can show that prin C, okay, so prin C, there, so this exercise would show that prin C, which is the set of all principal divisors, right? Things coming from rational functions, that this is a subgroup of the set of degree 0 divisors. Right? Awesome. And so now is the big definition, which is the first one is called the Picard group of C. This is defined as the set of all divisors on C modulo the ones coming from the principal divisors, right? So you quotient out by the set of principal divisors. And the second is pick 0 of C, which is also called the Jacobian of C. This is defined as the set of degree 0 divisors quotiented out by the principal divisors, right? So this is like the big definition, that the most important definition from this section, right? Knowing what big zero is. Okay. Any questions about this so far? Okay. So if you want, what you can do, so here are some examples of what big zero looks like. So okay, so if you look at the Picard group of C, right? This is all the divisors mod the principal divisors. There is a map from this to Z that sends D to the degree of D. And it turns out that there's actually an exact sequence, which is not very hard to prove, right? The ones that the kernel of this map is just the degree zero divisor, right? Excuse me. And so here are some things that you can do, right? So again, this does not require much background in algebraic geometry, just an understanding of what P1 means, right? So P1, you can show that also pick of P1 is actually isomorphic to Z, right? A divisor is so this would work. You can show this by showing that every degree zero divisor, right, is actually principal. The second one, so this is actually in the exercises, but it sort of like walks you through how to do this problem, is that the Jacobian of E is isomorphic to E, where E is an elliptic curve. Right? Okay. So this is actually a very, very cool thing, and also a very important isomorphism that like comes up a lot when you're talking about elliptic curves. I won't talk about this much right now because of the lack of time, but the notes and the exercises explain it a little more, right? So they give you a map from E to pick not of E, and then and explain that better. So I should say that sometimes I'm going to pick not of E of any C. I'm going to sometimes denote it by the Jacobian of C, right? They're the same thing, right? So this is just notation. Awesome. So now we're ready to define genus. Let's see how much I can do. So let's define the genus of a curve.
Soumya?
Yes.
There's a question. Can you explain why is the print C a subset of divisor, the zero divisors? So why the...
Okay. Yep. Yeah. So I left this as an exercise, but the way to think about this is the following. So if you look at a projective curve, so for instance, you can just you can think of the curve as being a curve in the plane, for instance, right? If you want, you can just work with one homogeneous polynomial in 3 degrees. Sorry, in 3 variables. And then what happens is these rational functions are defined as the ratio of 2 polynomials. They're g over h. And because you're on projective space, these have to have the same degree. So projective space implies that degree of g has to be equal to the degree of h. And so the number of zeros, which are going to come from the zeros of g, are going to be the same as the number of poles. Right? So because in projective space, remember, you can scale variables and you should still get the same answer. So if you scale variables, so both of these have to be homogeneous, and in particular, they have to be homogeneous at the same degree, otherwise this won't be well defined. Great question. Okay, awesome. So, Okay, maybe I have time for a quick aside. So if you have a curve over C, right? Um, over C. Um, so what is a curve over C? Well, it's a dimension one object over C, right? So what this looks like is a Riemann surface, right? So if you've seen some complex analysis, maybe you've seen a Riemann surface before, but if not, what this looks like is a glorified torus. Right? And the genus of the curve is just defined to be the number of holes. See? And if you've seen some topology, then it turns out that like the homology of this curve is sort of generated by two G generators, right? So I'm going to call this G, et cetera, et cetera. And you can, while this picture doesn't make sense over FQ, there is um, there is a notion of like homology and cohomology even in finite fields. And it turns out that the cohomology of a curve, the corresponding cohomology of a curve also has two G generators. So this picture, even though it doesn't make sense over finite fields, it's very closely related to what happens over finite fields, right? So if you want to take the equations of a curve and just think of it in terms of a curve over C and then count the number of holes, you would be okay. Don't, yeah, you would be okay. Anyway, enough philosophizing. Let's actually define genus. Um, so what I'm going to do is I'm going to talk about the set of differentials on a curve. And what this is um, this is kind of the set of differentials from calculus, right? So you have a bunch of equations in x and y, and then you want to take dx, dy, df, where f is some function on the curve, right? So let's say C is your curve, and you want to take some, if you take f, which is some function on the curve, then the set of differentials, a differential is a KC linear combination of such df's, right? So it's like, right, so you can think of it as like a formal sum of df, so like df plus dg, blah, blah, blah. Okay, and subject to the following conditions. First of all, you want it to be linear, so d of f plus g is df plus dg. You want it to kill constants, right? So d of a constant function should be 0. And most importantly, it should satisfy the Leibniz rule, which is d of fg, which is the product rule that you may have seen in calculus. So it's gdf plus fdg, right? So, so what this is, so this is called the Leibniz rule, right? So a differential, right, is just going to be a combination of these. So some f fi dgi, right? Subject to all of these relations, right? Um, so there is a way, so to talk about zeros and poles of a differential. And if I have time at the end of this, I'll talk about how you define these. And so because you could define zeros and poles, you can define the divisor of omega. So can define a divisor of omega. So if omega has no poles, then it's called holomorphic. Right? So this is very much analogous to the holomorphic functions or holomorphic differentials from complex geometry, right? So if it has no poles, then it's called holomorphic. And what I'm going to do is I'm going to collect only the holomorphic differential. So capital omega of C is going to denote the set of holomorphic differentials on C, right? So so what this is, and so this turns out to be a vector space. G is defined to be the dimension of this vector space. Awesome, great. Hopefully, so intuitively, I don't know if this is, I don't know if you see this for the first time, what you think of this definition or what kind of intuition it gives you. But the handle picture is the intuition you should have behind it. But this is how it's defined as the dimension of the vector space. So, for example, right, you can show that E. So let's do a quick. Right. So first of all, I want to define the divisors. So I promised you that it makes sense to talk about poles and zeros of a differential, right? So let's see what that means. So if you have omega, which is some differential on a curve, right? Right? So locally, so I'm going to write div omega tautologically as or d omega b, right? So the question is, what do I mean by the order of a differential at a point, right? That's the question. And so what you can do for a curve is that locally you can write a curve in one variable. So this is very much analogous to like the inverse function theorem in calculus, right? So or when you try to like parameterize a curve in calculus, like locally you can write things in one variable, right? So locally around P can write C in terms of one variable. Right? And let's say we call that variable T. So that means that the differential, right, which is the linear combination of all of these functions and dg's, where dg is also a function, you can write omega as some f of t dt, right? And so the order of omega at that point is just defined as the order of this function at this point, right? So f of t is something, it's got some zeros and poles, right? So order at t equal to 0 of f of t. Okay, so I'm out of time, but maybe I'll say one quick thing. So maybe an example will make this slightly better. So if you write y squared equals x cubed plus ax plus b, right? And remember, x was a function, right? So we can take omega to be dx. And you want to calculate the zeros and poles of omega, right? So let's say you're around the point, so let's say x minus e1, x minus e2, minus e3. So let's say you want to look at the point e1, 0, so p1 equals e1, 0. Then at this point, what happens is, right, so e1 is somewhere here. It turns out that this local variable in terms of which you can write everything is y. So you can write So y is the local variable, right? You can prove this using the inverse function theorem if you like. Is the local variable, which means that, so you can write x minus e1 as y squared times something that's a unit in the local ring at that point, right? So the unit basically means you don't have to worry about it. Its order is 0. So so that means that dx is 2y times the unit plus y squared times the derivative of the unit, blah blah blah, which means that the order of at this point p1 of dx is the same as the order of y at that point, right? And so y is a local variable, so that's just 1. Okay, so I think I'll stop there. Um, this example is fleshed out more completely in the notes, so you can look at that, right? So yeah, and I think I'll stop there. And tomorrow we'll discuss more things about Jacobian, etc., etc.